We are today very fortunate to have one of the old-timers who left the team relatively early and went back to Germany. But he spent the first few years with us in Fort Bliss, Texas.
No, 1 year.
1 year.
1 year and
in Fort
half,
Bliss, Texas.
3.5 years in
Right.
New Jersey.
And you probably all know that the main activity in Peenemünde was a V2, which we called the A4 at that time. But towards the end of the war, von Braun was also asked to develop for the Air Force the Wasserfall. And Klaus Scheufelen, Dr. Klaus Scheufelen, was really one of the employees who worked at that time for the Air Force. I think you were a lieutenant or an Oberleutnant.
On the first lieutenant.
And since the Wasserfall did not go too well, you also started to work eventually on the Typhoon.
Yeah.
And I think we will all appreciate it if you tell us a little bit, firstly, about the Wasserfall, because not too much is written about the Wasserfall. And I think besides your book, there's really nothing else available on the Typhoon. So we are all very much interested to learn a little bit more about the Typhoon. With that, I would like to turn the meeting over to Dr. Klaus Scheufelen, and he will tell us about his activities in Fort Bliss and also what he did after Fort Bliss, still in this country, before he went back to Germany. Klaus, it's all up to you.
Okay, you see, I am a chemical engineer from the Institute of Technology, Darmstadt. And my family is in the paper business and was one of the first companies which did coding. My father was a chemist and worked together with a development company of coding which was Dillon Collins in Philadelphia. And as I'm born in 1913, I could finish my study. I finished Darmstadt in 1937 and worked then in the industry. And there was a draft in Germany, but from 1914, my year had only was drafted twice, 2 months, and then with the beginning of the war, I came to the troop, to the anti-aircraft, the flak. And when it was necessary to develop guided missile, the program Wasserfall was started in Peenemünde. But the personnel working on this project came all from the troop, which means the troop organization was continued. And for certain groups, people were taken which had some military experience and some organization experience, but had a corresponding degree of work in this direction and had worked for some time in the industry. And by this reason, I came to Peenemünde and got the responsibility for the development unit of the Wasserfall, which the Wasserfall, to explain, was propelled by nitric acid. And there was some work done on nitric acid, especially by Dr. Thiel. If I have to explain the situation of Peenemünde, how it was at that time, the people of Peenemünde came from two sides. The one side were what we called people were going to the moon. On the other side there were the military people. And the military people were necessary because after the Treaty of Versailles, Germany was not allowed to build long-distance guns. So they started to develop long-distance rockets. And this development was mainly done by Dr. Thiel in Gunnersdorf. And with the continuing of the development, these two groups, the people, what we call the Werner von Braun people, who worked on rockets with the goal to go to the moon or to stop. And the military people came together in Peenemünde. And there were naturally two opinions. The military opinion was more for the nitric acid. I can later on explain why. And who wanted to go faster, they were for oxygen. The reason was that in the first stage, nitric acid has a lower specific impulse, but a much higher specific weight. So the distance with the nitric acid in the first stage goes faster than a rocket developed with oxygen. But in the second stage, it would be too heavy, and so it turned out that the development was turned over to the oxygen, which means in the early time, the E4 was not considered to be used in the war. It was for faster developments. But then with the situation becoming critical, it was used for military purpose, but practically for the public opinion in Germany. You see, one V2 cost was as expensive than a fighter plane. And to transport 1 ton of explosive with a chance of 50% and then hit about 6 kilometers to 2 kilometers didn't, from a military point of view, any sense. And so, but this decision was made after the situation in Germany became critical after Stalingrad. But this was why the V2 was on oxygen. But for anti-aircraft missiles, you have to fire to be available all the time. You have to store it. The development of nitric acid was faster developed. There was already a limited development in nitric acid with different fuels. The fuels were at that time self-igniting. And when I came to Peenemünde with a job to develop the propulsion unit, I found already some real basic work done on which I could continue. It was not a big problem to go faster. And the situation was that the design of the waterfall was ready, so we had so space available, weight available, and we had to get this propulsion unit work within these limits. And it was relatively not a hard job because theoretically everything was available, with one difference. There was an opinion that the combustion chamber had to have a fixed volume, and which was, I don't know why this happened. Naturally, with the pressure, you can reduce the production chamber with the third power. And waterfall was started like the E4 at that time, with a pressure in the combustion unit of 15 atmospheres and with the same specific volume. That was the temperature of the combustion chamber was lower, so it was relatively clear from the beginning that the volume of the combustion chamber was not big enough. But it was also the differential pressure between the original pressure and the injection was at the A4 6 atmospheres, and we needed for the waterfall only 2, so we could increase the pressure of the combustion unit from 15 to 19 atmosphere and got the necessary combustion velocity we needed for the volume. This was the first problem. The second problem was that we got the same vibrations the A4 had in direction of the flow. And there was a test stand with a 4.2 tons combustion unit where we could make trials, and we tried not to keep the combustion doing in the length the combustion, but putting both fuels together. So we had planes, and the combustions were together. And the reason we could do that, because the fuel was self-igniting and had a much higher reaction velocity. So it worked with just the efficiency was about 1% lower than in the project, but by increasing the pressure from 15 to 19 atmospheres in the combustion unit, we gained this 1%. So this work was in this part step by step, and we got also information. It was Dannenberg and Heller. We could talk about it. That worked relatively easy. Then, naturally, if you brain a unit, you try to do it with as little as possible possibility to have a defect. So the way this Wasserfall worked was you had a big container with high pressure, about 250 atmospheres, and then a pressure reducer to get the pressure of 21 atmospheres for the tanks. And the way it worked, you had the high pressure container, then you had a destructive valve, just two aluminum thin plates, and in between you had the fuse, and with some explosive, and you exploded this, so you got it working. Then on the top of the two tanks there were just also I don't know the English word, blood membrane. Aluminum plate which gets destroyed at 2 atmospheres. So there was a lot.
You call it burst diaphragm.
Yeah, so, at the top. Yeah. And the same we had at the end. And then it was the idea you have to, for ignition, you couldn't have, even at self-ignited, you couldn't use the full flow of the stuff, because then at the moment the ignition time, it took some time to self, it would have to be high. So we had to have a valve. And we called it programmatic valve on both sides. The next thing, the project was was exactly like the A4. The big the oxygen was running a little earlier. So here the situation was different. Nitric acid was nearly 4 times as much in weight as the fuel, by the different, and only part of the fuel worked on self-ignition. So we had to change the situation, and we started to work and found out that we didn't have to limit the fuel. We could start with the full flow of the fuel, but we had to limit the nitric acid. And the idea how it should be done, that the pressure was measured in the combustion unit, and in the moment the pressure went up by ignition, then the valve, the reduction valve for the nitric acid should open. And there we had a terrible problem. We worked hard and some explosion, which just didn't come ahead. And then we discussed it, and that why can we not do it also by a way of self-destruction? The injection blade was a braid, and the nitrogen came in by conical holes. Why not put around this thing, a band, a thicker band with a hole which will be absorbed by the oxygen. And the same time chemist for this fuel, Dr. Schinkel, he got very old. He just died. I met him 2 years ago up. He got a fantastic idea. He said we used one of these fuel was brenzcatein, pyrocatechol. So he said, I just I fill these holes with pyrocatechol and drill a hole in, which means the nitric acid reacted with this pyrocatechol, made a bigger hole, but the other important thing, increased the temperature. And the other problem we had, that self-igniting at low temperatures didn't work too well. It was very critical. We couldn't do less than plus 5 centigrades. And by this factor, the whole thing was heated up by about 30 centigrades, and we had no problems anymore. So we could forget the valve and could just two membranes which were destroyed, and then the control of the start of the combustion was done by destruction work. And from this point we had worked so well, from there we had no explosion of a combustion unit anymore than it was from that time. That naturally made the things much easier. We were practically ready with the development of the combustion unit, of the propulsion unit, and could start the trials together with control equipment. And the development of the controlling of the flight could be done in the test stand because fins in the jet fins. Mm-hmm. So things went relatively nice, and the first flight of the Wasserfall was 2 months ahead of schedule. On the first 6 starts, some problems happened, but they were all just mistakes. From there, the start of the Wasserfall worked good, but there came a new problem we didn't have considered at the end of the flight. At the end of the flight, the acceleration in flight direction was about 4g. But by moving the acceleration, you could move the thing around. It worked. We had no problem with the control, with the steering. It was 8. So when at the end of the combustion time, there was a strong acceleration horizontal, and the liquids went away from the hole to get out. So there was several ideas who changed that, but the problem was when the Wasserfall program was started, the idea was to control it by radar, but the German radars at that time based on a decimeter wave, and this decimeter wave was jammed by these aluminum stripes. So the control, the steering of the radar was not possible anymore, and the two homing devices which were in the development, they were not ready. So it was decided to stop the Wasserfall till this could be done. But the question came then, couldn't we use the experience of this development? Couldn't we use the experience of this development for other reasons? Now I have to come a little to the problems of the air war. The problems in the air war was that originally with the radars and with the situation, the air defense, especially by the flak, was very successfully. And they had about one success needed about 2,000 hits, 2,000 Granaten. 2,000 needed about 2,000. But by the jamming, this number went up to 8,000. Because, you see, 8,000, but on the other side, these air raids, it was the industry, were not successfully. But other air raids were very successfully burning of all cities, especially concentrate the air raids, mass air raids, and there was the idea, how can you prevent that in a situation where the jammed radar is not so bad, and that was on the oncoming flight. So the goal was not to fire from a gun, not one or one after the other, maybe 8 on one overflight, but 28 concentrated on the oncoming flight. And with the hope, as faster and shorter the flying time to the goal was, as the mistake went down, you see, the whole system based on this, that you measure what is doing now an airplane. But when the airplane changed, you were doing this 15 or 20 seconds, it didn't work. So the Typhoon was developed, and the base of the Typhoon was that you could do things which we found out doing the work. You can decrease the size of the combustion unit nearly with a third potential of the pressure. So it was possible to, you see, the Wasserfall unit had 19 atmospheres, 8,000 kg drive, and but a diameter of about 600 millimeters. And the combustion chamber of the Typhoon had a diameter of 92 millimeters, and it was possible to produce
Thrust.
What?
Thrust.
The thrust had a thrust of 1,500 kg. So it was possible to, the whole thing works this way. On the top there was a solid fuel which produced the pressure to take both fuels out of their tanks. The tanks were concentric, that were by several reasons. So it's the same thing, except the same. On the top was blood membrane, and the bottom was a blood membrane. It's the same as the Wasserfall. And then, because there was not space enough for this, you had to do to mechanical help to delay the flow of the nitric acid in the combustion chamber, and that was done in that way. There was at the end of the acid tank, there was a little blade which left only part of the nitric acid out, and this blade was connected with a blade in the combustion chamber, which took this blade out in the moment of ignition. And so it was relatively simple, and since we had also experience of the Wasserfall, it took just 4 months to develop the Typhoon and to make it ready for mass production. And it was relatively severe. You see, most parts were steel, and they were formed could be formed out of plates. At that time, they were the high pressure for performing of material was in. You could perform the combustion unit by high pressure production. You could make even the tube with 1 meter 30 length, 1 millimeter strength of the wall, and 100 millimeter outside diameter. So it was very easy to produce. These parts were all produced with presses, and then they were welded together with parts with Gewinde, with a
thread.
The way the Typhoon worked in the top, it had and the point was that I forgot to say. Originally, it turned out that if you go above a certain amount of Granaten, missiles, to hit is it better you have impact fuse than a time fuse? That is statistically very simple. You have 3 dimensions. If you have 8,000 missiles to hit an airplane, that means 20 in each dimension. And the airplanes became bigger, but they were not less sensitive. So somebody found out that by impact fuse it is better than to use time fuse. And at a time fuse, you see, you could fire from a gun out one missile after the other, and the whole Typhoon worked in this way, and that made it so easy. You put just instead of the barrel, a box with 28 missiles. On the A4 gun, and that was what you had to change. And the other what you had to change was the control form in the calculation unit. So you could change a battery within 24 hours to the use of the use of the Typhoon. And with the possibilities of December of 44, the planning was to build 1.2 million Typhoon a month. The biggest problem at that time was not the production, but the calculation, because you first had to shoot the Typhoon and measure it, the ballistic curves. That was ready about it, that we were in schedule about middle of February. The production started with planned 35,000 pieces, about 25 were produced in March. But then it needed time. You didn't have computers. So you needed about first 60 girls to calculate the final ballistic curves, and then calculate the form of what we call Kurvenkörper. You see what you put in the calculated unit, which you had to change. So the early start with the Kurvenkörper could be balanced, very easily produced by model Fräsen, Kopierfräsen. The same way we made the fins of the top. So the start of the 1.2 was planned in September, so 45, so it didn't work anymore. And then my contract when I came to this country was for purpose for this for anti-aircraft, but it took some time till the money was made by the Congress. So I was the first time, 1 year we were all together in Fort Bliss, and I worked since I had built test stands on the idea to measure a ramjet and to drive on the mountain.
Yeah, I think we use the term ramjet here.
Which should support 2.4 tons as far as possible, and with a ramjet unit.
Yeah.
And but about in early 45, in early 47, then the Typhoon project or the under-aircraft project was okayed, and but it was used not basically because from a military point of view the US didn't need it, but it was a very simple, small development where you could use all things. And one thing, it was just more accidental. It was not possible to increase the Typhoon very much from combustion or from these things. The only way to do it was by aerodynamics. So the idea was to the Loki, which based of the Typhoon as a booster, and then have a narrow, aero-stabilized, very long, heavy missile. The Loki had 3 inches, and this missile had only heavy with 900 grams explosive, but had only a diameter of 1.25 inches, and so at the end of the end velocity of the Loki was only 100 meters higher than the end velocity of the Typhoon, but since the air drag was much lower, the air drag was the weight, the ballistic pressure was much higher. The Loki project was possible, and that was proved. It worked in the wind tunnel, and the figures were all right. That it was about 60% in the end velocity, 60% after 30 seconds flight time faster and higher. And this this Loki development went away from propulsion, and in models how to transport a small load with then it was changed from nitric acid basically to solid fuels. The US didn't like nitric acid.
Yeah, that brings up the question: what's the advantage of liquids concerning in relationship to solid propellant?
Yeah, the higher, you see, the higher efficiency.
It has higher efficiency.
I know, yeah. You see, that's very interesting, and something happens, you see, sometimes happens story which you think that it cannot happen. When the Typhoon was work, somebody came to the and said he can do something similar with Mr. Burkhardt. And then Mr. Burkhardt was an engineer who had worked for the armed forces, after even till the 35, the Russians and the Germans worked very close together military, and he worked 12 years in Russia. And he came and said he could do the same or nearly the same with the liquid with propellants. But you see, there is one thing, and I think that still exists. The Russians had and have, according as far I consider, one big advantage. They can control the combustion of solids much better. You see, the problem of the solid propellants is that the combustion velocity is highly dependent on the temperature. And This Mr. Burkhardt came and said he can build the solid fuel Typhoon with 2 millimeter wall strength. According to the German experience, it would have also the American, it would have needed 3 diameter, because the temperature, you needed a much higher pressure to see solid fuel needs high pressures, 150 atmospheres. But the Russian limit was about 200 atmospheres, and the German American at 300. So I was a little, I said, well, I'm not quite sure. He had also a Russian wife. Isn't such this guy a style? No, he is not. And you see, since he was a very good man, and I needed somebody to expel, to give me the solid fuel, I gave him the value of the Typhoon, and I got the solid fuel to expel the liquids. Then we worked together. And then at the end of the war, he worked also on the Mittelwerk. He said he needed some money to dissolve his office, and he went to in Berlin, so he did it. But then it came out that he had passed the front line in Silesia. Then everybody knew that he was. But then, and that was crazy, after we had left the Mittelwerk, he came back, Rudolf, met him there, and then so the engineers, or the responsible for small rockets, and they were developed by the army. You see, Flak was Air Force, but the development was army, was an engineer size for small rockets. And he was worked together. He was responsible for our work, and he was brought together with him after the war by the Russians. And the Russians had the impression that he had some connection to the Eastern power, to the Western powers. So, well, Zeiss, he was put the DDR, he was sometime in jail, but it turned out that Mr. Burkhardt was Professor Zishinsky of the Institute of Technology in Leningrad, and had the Lenin buried. But from that time, they didn't trust him anymore. And so when he went back to Russia, together with his wife and secretary, he fell out of an airplane short before Leningrad. That is the story. But from that time, you see, and that is one of the big reasons. The Russians have are much more efficient, I would say, the solid propellants of the liquid propellants with a German or American value has about 65%. The liquid propellant is solid has only 65%, because by this high pressure you need this thick wall. You see, for the same, the Typhoon had just one millimeter wall strength for 60 atmospheres. And in the middle it had an aluminum tank with pressure on both sides. So the weight of the propulsion unit compared with a specific impulse is of liquid pellet compared with is about 65% of fuel, as it is with liquid with nitric acid. And the Russians are much better, and one of the reasons was that for the Sputnik, the first stage of the Russians, as far as I know, originally was solid propellants. That's so. That's the difference. It's just a question how the solid propellant can be improved at the same specific impulse if you get the pressure down, the maximal pressure. That is the difference. You see what we also had, but we had it in a in a small amount. It was not for mass, not use. We had also nitrogen tetraoxide, which is about the specific impulse is 6 or 8% better as nitric acid. Mm-hmm. And you see, if you now look on the developments, if you wanted to go not too far, just maybe to a satellite, you could say, well, I stay basically on a one-stage unit and help by some help. And that's the way the French did it with Ariane. You see, the French uses nitrogen tetraoxide and some help by, but the basic is still improved nitric acid. But you cannot go in several stages. But all the planning of the Ariane is do the maximum to make a satellite go to the equator to have a better start.
Yeah.
And by all these things, so yeah, that's all. But I must say, the end of the last 1.5 years, I worked on the Loki, and I made it. Then the problem came to find what happens. Aerodynamics at that time, there were a lot of different things, and by an accident, I came to the heat transfer. You see, by the factor that we didn't need to develop this valve, I had a lot of free time on one test stand. And so everybody who wanted to find some things said, well, can I try something? And Dannenberg wanted to build a combustion unit. Dannenberg was a man responsible for the combustion unit. Unfortunately, he died shortly after he came to this country. And the problem was on the narrowest part of the nozzle. And he wanted to inject fuel at this in this nozzle to additional cooling. So we made this trial, and this combustion unit with about it was 19 atmospheres lasted for 11 seconds. And later on, the test engineer came and said, we didn't have any injection because the hose were closed. So I said, well, now things become interested, which means now let's try to measure the heat transfer by putting measuring elements on the side and write them. Mm-hmm. And this was very simple, and we could measure it, but then it became very complicated, and we found out that roughly at the formula of Peckley, if you measure the heat transfer, you have a pipe, and at the beginning of the pipe, the heat transfer is about, by higher turbulence, 35% higher than after after 2 or 3 meters. And we came to the result that you see, the point was what happens in the going over to supersonic. And we said, we found out from our measurement, it doesn't go higher than if you have a pipe and at the beginning, according to Peckley. Well, and so I wrote these things, all the results together in a report, and then I was forced to get it calculated. And it turned out to be terribly complicated. So we had with us was come a professor from Darmstadt, Karl Wagner. He was a very good man. He was a chemist, but an excellent mathematician. And you could go to him and ask him, and he helped. And he moved then from the group of the rocket group. He was a professor at MIT. And so I had I had a help. You see, I was in Teterboro, New Jersey, and you see in my report, you find this formula, but he was never satisfied what I wrote. So every 6 or 7, 1 year long, he changed it. Mm-hmm. And finally, he was not satisfied, and after 1 year, he solved it by the equation. I put it in it. And it proves that I think from that time it is the conditions of what happens in the range of going from subsonic to supersonic is very clear. But I was forced, while I was working on now more on aerodynamics and how to, you see the Loki as was then has a possibility. He had the missile was 3 inches, but by the higher pressure, it had a cone at the end, and it had the arrow at the top had 4 inches, and with this way you could fire it from a gun with a Treibspiegel. You had a higher pressure. You see, that was missiles that were developed, where you have a higher area for pressure than the diameter of the missiles. And that was one possibility to improve the Loki. And then, because people didn't like nitric acid, the next idea was to get a bigger Loki with a Treibspiegel and 2 solid fuel stages. And this all these things goes back of an idea of Dr. Thiel to use a force, a V2 with nitric acid, and put it on a trailer of a submarine and fire it from a submarine. And at that time, the firing of a payload of a submarine was very in favor, and that was what I worked on. So that was my main work, my group. We had a test center on Dover Arsenal and the other things, but I practically didn't have the time to follow up what happens there. But this was very under pressure, and so when my contract expired in June 30th, 50, my family was already back, and the Korean War started. I stayed 4 months longer to try to find out how to calculate such a thing and to measure it in the wind tunnel. So
let me ask you a few questions after your remarks here. Firstly, he referred several times to his book, and maybe you want to take a big shot of the book, Mythos Raketen, and of course it's written in German.
Yeah.
So right now there is no translation in English available.
No translation in English.
Yeah, so it may come out one of these days.
No.
Concerning the Typhoon,
yeah.
I have a question. Did it have a guidance system?
No.
So no guidance system,
no,
that's why you wanted to have 48 units ready to be launched.
You see, theoretically, the highest efficiency of the under-aircraft is the oncoming flight.
Yeah.
And second, on the oncoming flight, you couldn't jam.
Mm-hmm.
You prevent the jam. The theoretical, the people thought, I think it was about the flying time, was about 70% of the 88. The statistics said this typhoon could, 2,000 typhoons were needed for a hit.
And you built about 40,000 typhoons, I think you said.
Well,
you built about 40,000 in Mittelberg.
That's about 40,000, but the plan was...
How many of those went to the front and were actually used?
Nothing to the front. You see, what the typhoon, the action stage was that the ballistic curves were finished. They needed about 1,200. And the result was compared with 3% lower. It could have been changed by making it a little longer, but it was decided to leave it that way. Mm-hmm. And to leave it that way, and so no change, no impact fuse, you see.
Yeah.
And that's the impact fuse. You see, you could fire it with a time fuse. You could fire only one because you had to put the time fuse on. The idea of the Typhoon was based on the actual values of the air war, and that they were different to the original. In the meantime, you don't have never. You have the Typhoon type of missile is used all over. It's all over, but naturally, you have the homing devices, and the small you don't need it anymore. The Typhoon was just for a limited period. Towards a period till the Wasserfall got a homing device. It was not it was an in-between solution for a special case, but it turned out that the work with the Typhoon and with the Loki, because it was relatively inexpensive.
Yeah.
A lot of basic developments were done, and we worked also then in this work together with some big companies, with General Motors, with the development unit of General Motors, with Charles Kettering. He was very interested. I had several times I talked to him, and so it was. It ended more in the calculations for aerodynamics.
And to come back to the Wasserfall, you pointed out the propulsion system.
What's right here?
And the main difference between the Wasserfall and the A4 or V2 is, of course, we had a turbopump. And you pressurize your tanks.
Well,
and you can do that because it's a smaller vehicle, and you save the weight of the turbopump and the drive of the turbopump, and so you can afford to build relatively heavy tanks.
You see, it didn't have to go too far, and at the Wasserfall, we had all except the pressure reducer, and it had to be not tight. Everything was went broke. You see, we didn't need any moving parts.
Yeah.
We all the smart membrane broke, everything, and there was nothing in which couldn't work. Statistically, what we didn't have considered was the acceleration at the end. But that would have been the solution would have been just to make a longer cone. So, but the Wasserfall, except 30, there were 34 starts of Wasserfall, except what happened at the end. The propulsion unit worked and the control system worked all the time. And that is because it could be very easily developed in the Prüfstand 9 by using the fins in the combustion chamber.
Yeah. And I think you pointed out earlier, based on the Wasserfall development, Dr. Thiel, whom you mentioned, Dr. Thiel, he also was working on an A4, on a V2 to be used with the same propellants.
Yeah, well, that was the point, you see, and then he put in a submarine.
In 43, we got a design freeze. So there was decided no changes anymore because Arthur Rudolph was supposed to produce the A4s. And of course you don't want to make changes while you are producing things.
You see, according to my opinion, with the result of we had, I had the opinion, what did you have to change on the A4 if you wanted to go to nitric acid? Naturally, you had to differentiate the size of your tanks. And you put the nitric acid tank in the top, So at the beginning, the center of gravity were much went up. The next thing what you would have to change, you could to get a blade like the injection like the Wasserfall, not the 16 tops anymore, so not just a big blade, which would have you saved on weight, and you see the first stage. You could leave it or could get rid of it.
Yeah.
You had the short stage at the end, you still needed it. But according to my opinion, it would have been possible. The question would have to be how, at that time, how to come fast along with the test stand.
Yeah.
But if we could have used the propulsion, the unit, or put in when we were safe that no explosion came in the test and 7.
Yeah.
Then it could have been done, and that was the idea of Dr. This was the idea of Dr. Thiel.
Yeah.
And
I think in the long run it would have been a good solution. You wouldn't have to depend on filling the logs, which was vaporizing all the time. So really to keep the vehicle on standby, which you would need for an anti-aircraft vehicle, it's of course very efficient. I mean, LOX is more efficient than anything else.
No, you see, it would have been that on my calculation, the calculation of Dr. Thiel, the A4 with nitric acid would have been 60 kilometers faster.
Yeah.
Longer. I must say the death of Dr. Thiel was a big loss. See, he was my boss because propulsion unit and test were his business, and he was very short. There was a problem and we were not quite sure. And he didn't say do that. He said, I would do it, but you are responsible.
Well, I think that's about it. Or are there any questions here from the audience?
Yeah. May I say something that I even have in English to the Apollo paper?
Go ahead.
Yeah? Okay. To explain the situation. Well, naturally, when I went back to Germany, and in my late time, I kept my mouth shut because for some time my work was highly classified. So I didn't visit any, my own interest. I had some protection for 2 years, but okay. And then when I read in the newspaper that they left the nitrogen away to space weight in the Apollo capsule, I said, okay, 1 kg per cubic meter, and if the part pressure of the oxygen is so right, it works. With the formula I explained, that you get the pressure, it's always the same pressure. And in this formula, on the one side you have the pressure, on the other side the temperature. But I didn't consider the second part, and not me did not only consider, but about 1 million engineers in the world who knew this formula and didn't consider what happened with the temperature. So when I read of this accident, which happened with the astronauts, the Apollo on ground, then and something you can think much easier in English, I just said, they forgot the heat sink. Well, the nitrogen is a heat sink. And if you take the heat sink away, the temperature goes up, and the temperature goes up with an E function very steeply. It's the same paper which just in natural air, if you take a drop of high material, which burns very slow, explodes. Then I got, after some time, a letter of Mr. Rees that they were looking for a paper which was not inflammable. You see, that is not possible. If something burns, you can delay it, but so since we are in coated paper, and in coated paper the percentage of not burning material is high. So I discussed with our development and said, well, why don't we make a paper which we put a lot more, we take the heat sink out of the air in the paper with more pigments. And with special pigments and some binders which are not organic. And we said, okay, we tried it, and we made because it's easier in the laboratory. You see, you have a lab sheeter and did it all together, and we found out what we thought what we could do, and so I made a quotation to NASA, 100 pounds of hard inflammable paper for $50,000. See, since I worked for the government, I knew how these things are made, and the test was, and the requirement that the paper had to work in the oxygen atmosphere exactly like the paper, normal paper in the air atmosphere. And it was even a little better. But now the problem came. You see, the purpose of NASA is not only to fly to the moon, but to get all the technologies which contributed. Mm-hmm. So the requirement was that we had to produce it on regular machines, and it was very complicated. And I said, well, we are not able to do that. I don't have the organization. I have nobody to work on the contract. So they said, well, we will give you a man who handles this for you. And he was a very experienced, good man. And finally, we got a contract, 5 tons of paper for 300,000. It was in marks, the ton. It became then very complicated, and I have here in a report of what we did. Let's see. And this is in English, so I can. So during that time, coating was also used for another very different purpose. There was no nitrogen in the Apollo capsule flying to the moon, which led to a much faster temperature increase after inflammation. The paper literally exploded, which led to the death of 3 astronauts during an experiment on ground. Adding special pigments to paper of a high coating weight enabled us to produce a paper reacting in oxygen atmosphere like ordinary paper in contact with air. Our knowledge in the decorative paper segment, producing highly filled absorbent papers, helped us enormously in that context. By also using flame retarding pigments, antimony 3 oxide, and soaking the high-filled paper raw material with flame retardants, we achieved fundamental progress. In order to be able to print on the salty raw materials, coatings were developed on both sides using a non-inflammable polyvinyl lithium chloride latex from BASF as a binding agent. In order to avoid coagulation of the coating during the coating process, a blocking layer was introduced by coating with sodium allignates with additional flame retardant properties. Thus, a satisfactory solution was found for the coating process that initially seemed unsurmountable. The moon paper produced by Scheufelen was first used on board of Apollo 13.
And how thick is the layer you put on?
Over there are different layers. You see the paper had a weight like, oh no, is that a question?
Is it about the thickness of the paper itself, or is it less?
Well, the layers were 1 or 2 grams. The cellulose was down to 45%.
Mm-hmm.
And non-burning material, there was one of the binders had a little burning material. But about 55% of the total was non-burning material and material which is fire retarding. You see, you can make paper by fire retarding by putting in ammonium sulfide, which is actually a fertilizer. Then it becomes fire retarding.
But
so
only retarding. Only retarding.
You cannot make there's nothing which burns which you cannot make unburnable. It reacts.
Particularly with pure oxygen.
You see, you can only delay. The question to say make a product which is burnable, a product which is burnable cannot make unburnable. That's the basic against the basic of physics and chemistry.
Okay, any questions? Did you even know about it, Chuck, that he supplied that kind of paper?
I had not known that.
It was new to me too. I never heard about it before he mentioned it.
Didn't know that.